Right now, you are standing on a giant rock spinning through space. Take a look at this rotating globe. It takes 24 hours to complete one full turn. This daily spin gives us our cycle of day and night, keeping half the planet in sunlight while the other half rests in darkness. But spinning is only one of the Earth's movements. At the exact same time, our planet is traveling on a massive oval-shaped path around the sun. We call this journey its orbit. One complete trip takes 365.25 days, what we experience as 1 year. Now, looking at this 3D model, you'll notice something surprising about how the Earth travels. It doesn't sit perfectly straight up and down. Instead, it leans over. There is an invisible line running from the North Pole to the South Pole, called an axis, permanently tilted at an angle of 23.5 degrees. This creates a strict golden rule for our planet. As the Earth travels its year-long path around the sun, the direction of that lean never changes. The North Pole always points to the exact same spot in deep space, no matter where the Earth is in orbit. Because this angle stays locked in place, different parts of the planet take turns leaning towards the sun. That permanent, unchanging lean is the invisible engine driving every season and climate pattern we experience. It is easy to assume that summer happens because the Earth gets closer to the sun, and winter happens because it moves farther away. But that is a myth. The Earth is closest to the sun in early January, right in the middle of winter for the Northern Hemisphere. So if distance doesn't create the seasons, what does? It all comes down to the angle at which sunlight hits the curved surface of our tilted planet. Watch how this simulation shows a beam of light hitting a surface straight on. When a hemisphere leans towards the sun, it catches the sun's rays directly. The energy is concentrated into a tight, bright circle. That intense, focused heat is what creates summer. But look what happens when the simulation tilts the surface away. The exact same amount of light strikes at a shallow angle. Now that energy has to stretch out into a wider, dimmer oval. Because the heat is spread over a much larger area, it feels colder to us. This creates winter. That simple geometry, determined entirely by our 23.5-degree lean, decides whether a region gets scorching, concentrated heat or weak, spread-out light. Twice a year, this tilt reaches its extreme limits. Around June 21st, the Northern Hemisphere reaches its maximum lean toward the sun. We call this the summer solstice. Watch the sun's direct rays strike the Tropic of Cancer. The North leans into the light, getting its longest daylight hours. 6 months later, on December 22nd, the Southern Hemisphere leans in. Direct rays hit the Tropic of Capricorn, giving the South its longest day. This geometry creates a strict rule. The seasons are always perfectly opposite. Leave is summer in the north, it is always winter in the south. These solstices represent the absolute extremes of our planet's heating cycle, pushing our daylight hours and our temperatures to their yearly limits. There is a halfway point between these extremes. On March 21st and September 23rd, the Earth reaches the midpoint of its orbit. On these 2 days, the axis leans neither toward the sun nor away from it. From space, you can clearly see the sun's direct rays hitting the equator perfectly straight on. The Earth isn't leaning into the light. Because of this, the divide between day and night cuts straight through the North and South poles, splitting the planet perfectly in half. Because the sun is centered perfectly, the light and dark are balanced. Every place on Earth gets roughly 12 hours of light and 12 hours of dark. We call these moments the equinoxes. These are the calm transitions of spring and autumn, a brief planetary reset before the Earth continues its journey, and that permanent tilt inevitably drives us back toward the seasonal extremes. To see how these massive movements in space affect daily life, we can look at the Indian subcontinent as the calendar moves from the balanced days of the equinox toward the extreme heat of the summer solstice. As the Northern Hemisphere gradually tilts toward the sun, those concentrated direct solar rays march northward. This acts like a massive furnace, superheating the vast landmass of India. This map shows the atmospheric reaction to all that heat. Hot air rises, creating a giant vacuum over the land. This vacuum violently reverses the normal wind patterns, pulling thick, moisture-heavy air off the Indian Ocean and dragging it inland. This explosive weather event is known as the southwest monsoon. From June to September, these winds dump enormous amounts of rainfall across the coastal regions and the Western Ghats. Without the Earth's 23.5-degree tilt shifting the sun's heat, these life-giving seasonal winds would never reverse direction to bring the rain. This celestial cycle comes with a brutal trade-off. Because the monsoon delivers almost all of India's water in just a few short months, the land is left parched and dry for the rest of the year. To survive this extreme wet and dry cycle, people living here centuries ago had to engineer a solution. They built massive water conservation structures known as stepwells or ballies. Looking at the incredible Chand Bowery stepwell, you can see the architectural brilliance required to outsmart the climate. These deep, inverted pyramids were designed to capture the brief torrential monsoon rains and store the water deep underground, keeping it safe from evaporating under the scorching solstice sun. This close-up of the repeating stone stairs shows the sheer scale of human effort required to reach that vital resource as the water levels dropped during the long dry months. It is a remarkable chain reaction. From an invisible lean in deep space, to the shifting of the ocean winds, to the digging of thousands of stone stairs, our daily lives, our weather, and our greatest monuments are forever tied to the movements of the earth.